to talk to you about a number theory formalization project in Lean. And everything that I will discuss today is joint work with Filippo Nucchi. So I should start by saying that I will not assume that you know what a local field is. This is something that I'm going to define because I know that everyone in the audience has very different backgrounds. But before getting to the definition, I want to explain a little bit how local fields fit into the bigger picture and give a bit of motivation as to why we care about them in number theory. So first, let me show you just a quick slide about some of the number theory results that we have formalized in Lean. By training, I am a number theorist. I did my PhD in algebraic number theory, and I started doing formalization about 3 years ago. So most of the formalization work that I have done is related to number theory. And Lean is a very good system to formalize number theory because it's one of the systems that has, or maybe the system that has most results available about number theory. So today, I'm going to talk about the beginning of this local cluster theory project. This is a long-term or medium-term project that I have with Filippo Nucchi, where we are trying to formalize local cluster theory, which is some subfield of number theory where you are trying to understand the maximal abelian extension of a local field. So of course, we cannot formalize local cluster theory or talk about local cluster theory without first talking about local fields. So that's the first step. That's what I'm going to discuss today. But then we are interested in formalizing this local cluster theory and because it has applications to many other areas in number theory. So for example, this is used in the proof of Fermat's theorem, and it is also used in Iwasawa theory to prove one of them, to prove the main theorem in that theory. Okay, so as I said, I'm going to explain the beginning of this project, of local cluster theory formalization project, but I want to relate it to some of the things here. So in this talk, very quickly, the p-adic numbers are going to come up, and we'll see why. So this is one of the first number theory themes that was formalized in Lean by Rob Lewis in 2019. And then in our project, we are also using results from this project about formalizing Dedekind domains and class groups, and also some theory about valuations that I developed in the project about formalizing adders and iders. And it's not relevant for today's talk, but also when we continue doing local cluster theory, we will also need some of the group and Galois cohomology theory that Amelia Livingston is developing. So this is just to put the project in a bit of context. The next thing that I want to do is give you some concrete motivation of where local fields come up in number theory. So for that, we are going to look at Diophantine equations. So historically, the first problems in number theory were trying to understand the integral solutions to equations with integral coefficients. Right? So we have something, for example, x squared plus y squared plus z squared is equal to 0. We want to understand whether this has integral solutions, or maybe we want to understand whether it has rational solutions. Okay, so in this case, we can use a positivity argument to check that there's only the trivial solution, right? Because we know that for any real number, the square of the real number is going to be non-negative. So in this case, x squared, y squared, and z squared are all non-negative, which means that the only way that this equation is satisfied over the real numbers is if x, y, and z are equal to 0. So then, because the integers are inside the real numbers, we conclude that 0 is also the unique possible solution over the integers. Okay, so sometimes to understand a problem about the integers or about the rationals, it is enough to consider that problem inside the real numbers. But this isn't always the case, right? So in the next example, I have changed the equation a little bit, and now I have a minus sign there. So a positivity argument, like we did before, is not going to work anymore, right? So this has real solutions. In fact, it has infinitely many real solutions. So, for example, the square root of 301 will be a solution for this equation. So we cannot use the same argument as before, which was saying, okay, we only have one solution in the real, so we only have one solution in the integers. But now we have not listed all of the real solutions, so it's possible in theory that some of these solutions could be integers. So we have to do something else to discard the existence of integral solutions. And in this example, because of these 3 that we have in the equation, perhaps a natural thing to try is let's look at solutions modulo 3. So we consider F3 or set modulo 3, which is the field with 3 elements. So the elements in this field F3 will be 0, 1, 2, and then 3 will be equal to 0. Okay, so we are doing arithmetic modulo 3. If we look at all of the possibilities over this field, well, in that field, 3 is equal to 0. So the equation is just x squared plus y squared is equal to 0. And then we consider all of the possibilities. So 0 squared is equal to 0. And then 1 squared and 2 squared are equal to 1. So if you look at all of the possible combinations, you will see that there is no way that x squared plus y squared is going to be 0 unless both x and y are equal to 0. But then you could say, okay, maybe it could be the case that x and y are equal to 0 over f3, and that would mean that they are both divisible by 3. So to conclude the argument, then you will see that the power of 3 that divides x squared plus y squared will have to be an even power because of the square, but then the power of 3 that divides 3z squared will have to be an odd power. Right? And that's how you conclude that this is not possible unless all of the values are equal to 0. Okay, so this is just an example in which we could not discard the existence of non-trivial solutions using the real numbers, but we are able to do it working modulo 3, working over the field F3. Okay. But somehow R and F3 are very different. Like R is an infinite field and it contains the rational numbers. F3 is a finite field. It has a very different feeling from the real numbers. So perhaps it's not the best analog to work with. And this will also be shown by the next example. So in the next example, it's kind of similar to the other two. Now, we are considering the equation x squared plus y squared is equal to z squared. And we want to show that if we have a solution a, b, c to this equation, then a times b times c has to be a multiple of 4. So now this is some divisibility claim, right? Like I'm claiming that ABC is divisible by 4, and the real numbers are a field. It's not clear that I can get any information about divisibility working in the reals. Right? So instead, we are going to try to work modulus on prime, like we did in the previous case. And now, because we are asking something about 4, the prime to consider will be 2. If we consider all of the possibilities modulo 2, that means x, y, and z can only take the values 0 or 1. We cannot really conclude anything too useful. We cannot conclude that ABC is a multiple of 4, just that it is a multiple of 2. But you say, okay, perhaps this is fair because you are asking a question about whether this is a multiple of 4, so perhaps you have to consider the equation modulo 4, not just modulo 2. So we can also do that. So we do case analysis in set mod 4. Set mod 4 will be 0, 1, 2, 3, and then 4 is again equal to 0, 5 is again equal to 1, and so on. And then you can also consider all of the possibilities. There's finitely many possibilities, right? And after you do that case analysis, you still cannot conclude that ABC is a multiple of 4. But if you go a bit higher and you consider the next power of 2, so you consider set mod A, and you do a case analysis, you consider all of the possibilities for x, y, and z modulo A, then you will see, you will be able to conclude that the product ABC has to be divisible by 4.
Why doesn't doing it mod 4 work?
Well, you will have to consider all the cases, but essentially what happens is that 1 square and 3 square are equal to 1, and then 0 square and 2 square are equal to 0. And so the only information that you are going to conclude is that this has to be a multiple of 2, but you will not conclude that it has to be a multiple of 4. Okay, so this is an example where working modulo 4 is not enough. But if we go a bit higher, we go modulo 8, then it is enough. Okay? And this is something that happens sometimes in number theory. Sometimes working mod some prime p is not enough. So maybe you have to consider p squared, or maybe p cubed, or maybe you have to go even higher. And for some problems, it's not enough to stop at some finite level. You actually have to look at what's happening at every power of p. And for that, we use something called the p-adic numbers. So sometimes to study a problem over the rational numbers, you will first try to study that problem over the p-adic numbers. Okay, so I'm claiming here, I'm not defining them yet, I will define them in a few slides, but I'm claiming here that the p-adic numbers are the correct analog to the real numbers when you are considering these kind of problems. And this is because, well, if you think about how you define the real numbers, well, there are several equivalent constructions, but one of them is you complete the rational numbers cube with respect to the usual Euclidean absolute value. Right? So you look at equivalent classes of Cauchy sequences, and then you throw in all of the limits of these sequences. You can do the same with respect to other absolute values. So what happens here is that for every prime number p, you can define a p-adic absolute value. I will give you the precise definition later, but for now I am only going to say that in the p-adic absolute value, p is small, and being divisible by p means that the number is small. So essentially the idea is that e to the n goes to 0 when n goes to infinity, or something that is divisible by p to the n goes to 0. Okay, so we do the same construction, we take q and we complete now with respect to this new p-adic absolute value, and that is going to give us a new field. This field is denoted qp, and it's called the field of p-adic numbers. And it plays the same kind of role as R. So it's a completion of q with respect to some absolute value. You can actually show that these are all of the possible completions because every absolute value over q is either the trivial absolute value or it's equivalent to one of these. Okay, so we have considered all of the possible completions. Okay, so QP is the first example of local field that we are going to consider. I'm going to give you now several definitions of local fields. So I'm going to start with the definition of a mixed characteristic local field. And this is just a finite field extension of the field QP of p-adic numbers for some prime number p. Okay? So I'm showing you here how to write this definition in lint. You start by fixing a prime number p and a field k. And then to say that k is an extension of QP, we use this algebra QPK. And then we have to impose the condition that the extension is finite. So for that, we use finite dimensional QPK. Okay, so this is one definition of the first kind of local fields, which will be finite extensions of QP. There is another kind of local field, which are called equal characteristic local fields. I will explain what mixed and equal mean later, but for now I will say that an equal characteristic local field is a finite field extension of the field fpx of Lorentz series over fp for some prime number p. Okay? So yeah, the definition over lint is very similar to the previous case. We have a prime number p, we have a field k, which is an algebra over the Lorentz series, which in lint we are representing as this type fpx completion. I will say a bit more about that later. Yeah, and we just have to impose the condition that the extension is finite. Okay. Okay, so we have two different definitions of two different cases of local fields. The definitions are quite concrete. We are just saying that this is defined as a finite extension of some other field. But there is also a more abstract definition that includes both of these cases. So I will read the definition and then I will explain what everything means. Non-Archimedean local field is a field complete with respect to a discrete valuation and with finite residue field. So everything that is in red right now is something that I have not explained yet, but I'm going to explain in the next few slides. For now, I just want to clarify 2 points. So the first one is I'm saying non-Archimedean local field instead of just local field. This is because sometimes in the literature, the real numbers and the complex numbers are also included in the definition of local fields. But for today's talk, I'm only going to consider the other cases, the non-Archimedean case. So I will just say local field. And then the second point that I want to make is that we have formalized this definition, and then we have also formalized the proof that a mixed characteristic local field is a local field in the sense of this abstract definition, and same for the equal characteristic case. You also have a theorem, a classification theorem going the other way. So there is a theorem that tells you that every local field is going to be of one of these 2 kinds. But that one we have not formalized yet because we haven't needed it so far. So the reason we want to formalize these 2 is because there are many results that apply to both cases, right? And we don't want to have to formalize the proofs separately. We just want to prove everything that we can for this general local field definition, and then we can apply it to both cases. Okay. So now I have to explain these 3 keywords in red. I'm going to start by explaining what discrete valuation means. Okay? So for that, I will first give you the definition of valuation. So a valuation V on a ring R is going to be a map from the ring R to some linearly ordered commutative group with 0, gamma naught. So what that means is you start with some commutative multiplicative group. You add a 0 element to that group that will satisfy the usual conditions that you expect for 0, like 0 times every element is equal to 0. And then you assume that this is linearly ordered and that 0 is the smallest element with respect to this order. And for the purposes of this talk, you can forget that I just said linearly ordered commutative group with 0, and then just pretend that gamma naught, this codomain gamma naught, is either the non-negative real numbers or some subset of the non-negative real numbers. So this is not true for all valuations, but it is true for all of the valuations that I will consider today. Okay, so we have this map V from R to gamma naught. For this map to be a valuation, it has to satisfy the following properties. The valuation of 0 is equal to 0, the valuation of 1 is equal to 1, the valuation of the product is the product of valuations, and then it satisfies something called the strong triangle inequality. So the valuation of the sum is less than or equal to the sum of the valuations.
Max of the valuations?
To the maximum of the valuations, yes. So if we are in this situation where gamma naught is the non-negative reals or some subset of the non-negative reals, in particular, you will notice that this is an example of an absolute value. Right, because the properties of the definition of absolute value will be exactly the same, except that here in the last condition, instead of asking that the valuation of the sum is less than or equal to the maximum, you ask that the valuation of the sum is less than or equal to the sum of the valuations, which is a weaker condition than this one. Right, so this is a stronger case of the definition of absolute value. Okay. So an example is the p-adic valuation. So let's look at this. We start with the ring R of integer numbers, and we fix any prime number p. Then we first are going to define some additive valuation. So this is going to be a function from a ring of integers to set union infinity. And this is defined by, well, we send 0 to infinity. And if we have any number r, which is a non-zero integer, we are going to define the additive p-adic valuation as the exponent n, which is such that p to the n is the maximum power of p that divides r. Okay. So for example here, if we look at the 3-adic valuation of 18, 18 is equal to 2 times 9, so 2 times 3 squared, which means that the 3-adic valuation of 18 will be equal to 2. Now, once we define this on the integers, we can extend this to a function over the rational numbers. And the way we do this is by saying that the additive valuation of a fraction, r over s, is the additive valuation of the numerator minus the additive valuation of the denominator. So for example, if I now consider the duadic valuation, so the prime is equal to 2, and I consider the rational number 5 over 16, well, the duadic valuation of 5 will be equal to 0, and the duadic valuation of 16 is equal to 4, so the duadic valuation of the fraction is equal to -4. Okay, now this is not a valuation in the sense of this previous slide here, because this is an additive function, not a multiplicative function. But to get a multiplicative version of this definition, what we do is we define a new function vp from q to integer powers of p union 0 by sending a rational number x to p raised to the negative of the additive valuation. Okay. Now, it's easy to check from this definition that this valuation function vp satisfies all of the conditions in the previous slide. Okay. And this is what we call the p-adic valuation or the p-adic absolute value. One technical point here is that in MATLAB, in our formalization, the codomain for this valuation is not going to be exactly p to the z union 0. We are going to use some abstraction of this, which is the type with 0 multiplicative set. So what this means is the integers set have an additive structure. You can consider the multiplicative version of this additive structure. This will be essentially like considering some kind of exponential function, but with the difference that here you have to fix the base p, and here you are not making that choice. Okay, but for your mental model, you can pretend that multiplicative set is something like p to the z, and then we add a 0 element. So yeah, whenever you see z times 0 in the slides, you can translate this as p to the z union 0. Okay. So to give you some intuition about the p-adic valuation, these are some pictures about some balls in this topology. So of course this is not a real picture because this is something that I'm drawing in the plane, but I will explain what it means. The gray circle in both of the pictures represents the ball of elements with p-adic valuation less than or equal to 1 for the prime p is equal to 3. Okay? So in particular, all of the integers will be contained in this ball. Okay? And then you can consider smaller balls. Remember that all of the valuations are of the form p to some power, right? So the next valuation is going to be e to the -1, so 1/3 in this case. So you get 3 balls of radius 1 over 3. And these 0, 1, and 2 represent the remainder when you divide the number by 3. Right? So in this ball 0, all of the elements are divisible by 3. Here they are divisible by 3. Is a number that is 1 plus something divisible by 3. And here is 2 plus something divisible by 3. And then you can continue doing the same thing. So now the next thing will be to consider balls of radius 1 over 9. And you see that you get kind of like a fractal situation going on. Now you see 3 balls inside each of these. And you can continue this forever. And yeah, so something that you can get from these pictures is that, unlike in the Euclidean topology, in the p-adic topology, if you have 2 balls, either one is containing the other one, or they are disjoint. And then something else that you have in this topology that is not true in the real is that all of these balls are open and closed for the topology induced by the norm. Okay. Are there any questions?
Maybe a silly question, but so are there things that are in yellow but not in green, or that are in gray but not in the yellow balls?
No. No, it's just the picture is not perfect. Yeah,
Yeah, we're just trying to understand.
Sure. Yeah. Okay. So now I've told you what evaluation is. Now a discrete valuation is going to be a valuation from a field K to this set M0, which remember is supposed to represent K to the set union 0. And we ask that this valuation is surjective. Sometimes in the literature you only ask that the codomain is set M0, but you don't ask for surjectivity. But we decided to ask for surjectivity so that we don't have to worry about equivalent valuations. We can just always worry about the normalized one. So this is the definition in LEAP. The valuation V on the field K is discrete if it is a surjective function. So, for example, the periodic valuation on Q is a discrete valuation, and the x-adic valuation on FQX, which are fractions of polynomials with coefficients over FQ, this is also a discrete valuation.
Can you say something about what's the motivation of calling this discreteness? This is an interesting condition.
Because the codomain is set for the additive version, right? So set is discrete.
Oh, so it's not about being surjective, but about the fact that the codomain is Z, rather.
Right. So sometimes you don't ask for surjectivity in the definition. If you ask for surjectivity, you are talking about a normalized discrete valuation. Again, the discrete makes reference to the fact that the codomain is set.
And non-discrete ones would have like R or something.
Yeah, something bigger. Yeah. Okay. Okay, so now I've told you the first part of the definition of local field. I told you what a discrete valuation means. I'm also going to tell you the second bit. So we have seen that a discrete valuation is in particular an absolute value. So you can consider the norm and the distance induced by this absolute value, which means that you have a metric and you have a topology. Right? So when I say that the field is complete, I mean that it is complete for the topology induced by the valuation. Meaning that Cauchy sequences occurs inside K. Okay. So now the last bit is what does it mean to have a finite residual field? So finite is clear, but I have to define what the residual field is. So for that, first I'm going to define the unit pole. I showed you an example before with these pictures, right? But the unit pole of evaluation is just going to be the subring of elements that have valuation less than or equal to 1. So some examples here. If you consider a cube with a p-adic valuation, then the elements on the unit pole will be fractions R over S, which are reduced, and in which p does not divide the denominator. Okay? So it's not just the integers, it's something bigger than the integers, because you are allowing denominators, you are just not allowing p's in the denominator. And then the unit pole of QP for the p-adic valuation is called set P, and this is called the ring of p-adic integers. And for the other example, if you consider the unit pole of FQX, which remember are Laurent series over FQ, then you will get the ring of formal power series over FQ. Okay? Okay, so this is the unit pole. Now, the maximal ideal of the unit pole, there's only one, you will explain that later, and it's given by the elements of valuation less than 1. Okay? So, for example, for the p-adic valuation, the maximal ideal is the ideal generated by P, and for the x-adic valuation in the power series ring is the ideal generated by X. Now, the residue field of a valuation V on a field K is going to be the portion of the unit pole by the unique maximal ideal. So, for example, the residue field of QP will be set P modulo P, and this is isomorphic to the field FP with P elements. And similarly, the residue field of FQX will also be equal to FQ. And now we can make sense of this mixed characteristic or equal characteristic notation, because in the first case, where we have a mixed characteristic local field. Remember, this is a finite field extension of QP. Then in that case, the field K is a field of characteristic 0, but the residue field is a field of characteristic P. But in the second case, when we have a finite extension of FQX, both the field K and the residue field have characteristic P. Okay, so that's what justifies the notation. Okay. So now I can finally show you the complete definition. We have said what the residue field is, so we just have to impose the condition that this residue field is finite, and then we are ready to write this in lin. So a local field is a field K with a valuation. So this valued class that we use in lin, this says that we have a valuation on K, but it also encodes the information that we are putting a topological structure on K, and that this topological structure is coming from the valuation. It's the one induced by the valuation. Okay. So yeah, we have a field with a valuation, and then we are asking that the field is complete for this topology. We are asking that the valuation is discrete, and that the residue field is finite. Yes.
So the valuation is a type-class argument, but it's also named. Is there? Well, why is it a?
Oh, it's named because I'm using it here. So it's just for convenience I want to refer to it.
Well, so more about the type-class part. Is there? I'm assuming there's more than one valuation that you can put on K. So there's like a canonical choice. I'm wondering how it interacts.
So it depends. So if you ask that this is complete, then there's really only one valuation.
So that's why it's a type-class rather than like a specific.
Right. So for example, no, but that's a very good question, because for example, on the rational numbers in Q, you can put many valuations. So I will not make any of these valuations be a type class, right? Because you can have the p-adic valuation for any valuation p. But in the p-adic numbers, really the only valuation that makes sense is the p-adic valuation. So that's why we make it into an instance. Yeah. And the name is that, so that we can refer to it. Okay. Yeah, so we formalize the definition, and then I will explain whatever I have time to explain about some of the basic theory that we have also formalized. So I will say that for the kind of results that we are looking at right now, this last condition that the residue field is finite is not needed. So they hold in greater generality, they hold for any discrete valuation, any field with a discrete valuation, or sometimes any field which is complete with respect to a discrete valuation. So because of that, and because in math we want to have things in the correct degree of generality, we are not formalizing the results only for local fields, we are formalizing them in greater generality whenever we can. Okay, so I'm going to give you an overview of some of the results that we have formalized about fields with a complete valuation. Okay, sorry, with a discrete valuation. Okay, so the first thing that I want to talk about are uniformizers. So if we have a valuation V in a field K, we say that a uniformizer for the valuation is an element which has additive valuation 1. And I realize that I have not explained what additive valuation means exactly, but think about the additive p-adic valuation. So I'm saying that it's 1 in that sense. Okay. When we formalize this, we are not working with the additive version, we are working with the multiplicative version. So that's why this looks a bit different, right? It's if you remember the p-adic valuation, this was p to the negative of the additive valuation, right? So this is kind of what's going on here. If something has additive valuation 1, then it has multiplicative valuation p to the negative 1. So a uniformizer is going to have valuation multiplicative of negative 1, so which basically means p to the negative 1. Okay, so we give two versions of the definition. We give the predicate version is uniformizer, and then we also have the bundle version where we pick an element of the unit ball, because if something has multiplicative valuation, sorry, additive valuation 1 in particular is in the unit ball, and then we ask that the valuation is exactly this, so that it is a uniformizer. Okay, why do we care about uniformizers? Well, you can show that a valuation in a field is discrete if and only if there exists a uniformizer for the valuation. So this is something that we have formalized. Here, K-naught is notation for the unit vol. And first, we formalize the claim that if we have a uniformizer, then the valuation is discrete. And then in the second lemma, that if the valuation is discrete, we can produce a uniformizer. Now, another reason why uniformizers are important is because if you have a valuation with a uniformizer or a discrete valuation, then any non-zero element of the unit vol can be written in this form. It can be written as power of the uniformizer times a unit. Okay? And this is kind of a powerful result. So, for example, it allows us to conclude then that the maximal ideal is generated by a uniformizer, by any uniformizer that you pick. And then it will also give us some more information about the unit vol. So, next thing that we formalize is that if you start with a field with a discrete valuation, then the unit vol is a discrete valuation. So what does that mean? A discrete valuation ring is an integral domain, meaning that it has no zero divisors, which is local, meaning there is only one maximal ideal. And it is a principal ideal domain, so every ideal is generated by only one element, and it is not a field. That will be the definition. And really what I want you to take away from this definition is that it has discrete valuation in the name, but it does not refer to a discrete valuation at any point. Right? This is the definition of discrete valuation ring that is formalized in MATLib. In fact, there are several equivalent formulations that are formalized, and as well as the equivalence between the definitions. But none of the formalized definitions in MATLib right now refer to the connection with discrete valuations. So this is something that we added in our project. So so we go both ways. So first here, if we have a field K with a discrete valuation, we prove that the unit vol is a discrete valuation ring. So this is the formalization. The first condition is showing that every ideal is generated by only one element. This is done using this characterization theorem, basically. And then the other two are very easy. So showing that this is a local field, link can deduce this immediately, and showing that it's not a field is also very easy. Yes?
Is a principal ideal ring a principal ideal domain? Is that a MATLib name for a POD, or what is a principal ideal ring?
I mean, yeah, I think that's a MATLib name probably, but yeah, like it means all ideals are principal.
What is the actual definition of not a ring? Or not a field, sorry. Like when it says not a field, like what is that?
Oh.
How is that written?
It's written as not is field in the MATLib definition.
Oh, is
so there is an is field definition, which means that everything is invertible except for zero, right? So it's written as not is field. So there's some element that doesn't have an inverse. Okay. And then we can also go in the opposite direction. So if we start with one of these discrete valuation rings, in the sense that I defined in the previous slide, we look at the fraction field of this ring. So fractions of elements in this ring A. Then we can put a discrete valuation on this field. And this discrete valuation is going to be essentially the same as the p-adic valuation, but the role of P is going to be played by the maximal ideal of the discrete valuation ring, which is unique because a discrete valuation ring is in particular a local ring. Okay? So, so we put this valuation on the fraction ring, the valuation corresponding to the maximal ideal, and then, so this is something that I had already done in a previous project, but what we did in this project that is new is we showed that this is, in fact, a discrete valuation. And we show this by applying the fact that we have a uniformizer for these values. Okay. Any other questions? Okay, so one of the first things that we did was relating this notion of discrete valuation to the existing notion in matrix of discrete valuation green. Another thing that we did is now restricting ourselves to fields with a discrete valuation that are complete with respect to the topology induced by this discrete valuation. We wanted to study extensions of these fields. So if you have a field K complete with respect to a discrete valuation V, and you have a finite extension L over K, then you can show that L has a unique discrete valuation W that induces V, and also that L is complete, again, with respect to this valuation. Now, this is, in fact, quite a complicated proof. I'm not going to get into the details, but I want to give a quick sketch and signal some places in which this formalized proof is significantly more complicated than the pen and paper proof. So the way that this argument goes is, first, I had proven in a previous project that whenever you are in this situation, you can prove that L has a unique valuation W prime, which doesn't take values in set M0, it takes values in the non-negative reals, that extends the valuation V, meaning that for every element x in K, V of x will be equal to W prime of x when you regard x as an element of L. So this is something that I had formalized in even a bit more generality than what we have here. And this was already quite a long formalization project. It's done by constructing, you first construct some kind of function on L, which is not quite a valuation, but then you generate several associated functions, and the last of these functions satisfies all of the required properties of being a valuation.
When you mentioned that you're mapping it into, you're saying that V is equal to W prime on elements of K, you also have to handle the codomains, which are different, right? Because this one is ZM0 and that one is R0.
Yes. So you have
P or something?
Sorry?
You have to say like P to
you
the
have to
nth or
pick
something.
an inclusion of set M0 in the non-negative reals.
Does that involve some particular prime or?
Yes, you have to make a choice. There is a natural choice to make. So if you are working with something like UP, but in general, you might have to pick something. When I formalized this project, I was actually working from the beginning with things that have a codomain non-negative R, because it was some more general setting. But yeah, here we have to make a choice. And that's kind of where the problems are going to come from, because what happens here is that the reason that we have these non-negative reals in the codomain is that in order for the valuation W prime to extend V, it's not possible that the codomain is just set M0. It has to happen that some elements of L are actually some powers of some fractional powers of elements of set M0. Right? So if you, again, if you think of the example of the PR evaluation, and maybe we are thinking of some finite extension of QP. So here we have a valuation VP, and this is going to take values in P to the set M0. Then here we have a finite extension, then this W prime will take values in P to some set with some denominators, right? Union C. It takes values somewhere P. And then once you have constructed this version of the valuation, now if you are reading this argument in any book, they will just tell you, okay, now you renormalize and you can get something discrete. This is very clear, but it's not immediate to formalize because you have like all of these different types going on. Like this is not a type that we have, right? Like you cannot consider, so if you have something in set M0, you cannot take a root of this element. So this is something that I have written here in quotes because this is not an existing type, right? So in the second part of the argument, you have to be very careful about making sure that everything, like all of the inclusions are working well together and everything is falling in the right place, essentially. So yeah, this was one point in the formalization where one line in a pen and paper argument becomes many lines in the formalization. But it is possible to do it, so we are able to renormalize W prime so that we can obtain a new valuation W, which in fact is surjective onto sequencing.
It's a silly question, maybe I'm not getting the point, but so you said that it is more difficult to make the proof since the type is not included in the formalization?
Well, I mean, it just doesn't make sense in right? Like this is something that,
why,
because
why not to extend the definition of the types?
So when you have an element of set M0, it doesn't make sense to take a root of that element. It's not an operation that is defined.
Okay.
So the workaround about this is we include both set M0 and what surrogate is inside the non-negative reals, because there you can do all of the operations. Yeah. Maybe it's not the only workaround, but this is how we did it. Okay. So this is something about complete fields. The other point here is that if we have a similar setting as before, we have a field K which is complete with respect to a discrete valuation P, and we have a finite extension, then the integral closure of K naught inside L is equal to L naught. So the integral closure means you look at monic polynomials over K naught, and you adjoin all of the roots of these monic polynomials. So yeah, we proved that this integral closure is equal to the unit ball in the bigger field. So in particular, we know that unit balls are discrete valuation rings, so we get that this integral closure is also a discrete valuation ring. Okay. Something else that we did is we defined ring of integers. And in the mixed characteristic case, the ring of integers of a local field K is the integral closure of the p-adic integer set P inside of K. So we get for free, because of the previous slide, that this ring of integers is a discrete valuation ring. And then I will not stop here, but we do the same thing in the equal characteristic case. I think I'm going to skip this probably. We have some results related to localization, but I can tell you if anyone is interested later. I have some implementation remarks. So first, to give you an idea of how big this project was, it took us about 8,000 lines of Lin3 code. We started in Lin3 because it was the standard when we started the project, but now everything has been ported to Lin4, and we are preparing the project to Massive. Some of the results are already in Massive. And this is a project that uses results for many different parts of the library. So we needed algebra, topology, and analysis for different parts of the project. So in that sense, it was very nice to have a unified library that has everything contained in there. And we also needed to use a previous project of mine for this argument that I showed you before. Something else that I will say is that if anyone here is used to the p-adic numbers, you might have noticed that I'm not using the notation for the math with p-adic numbers. I'm using some different notation. And that's why, because we are not using the same definition. We are using something that is mathematically equivalent, but is not definitionally equal. So in Massive, the p-adic numbers were defined before we had any theory of valuations. And probably because of that, they are defined by taking Cauchy sequence completion.
Okay. Sorry, you said before we had a theory of what?
Valuations.
Valuations, right. Okay.
So before having even the definition of valuation, we had the p-adic numbers. So yeah, so they are defined as using Cauchy sequence completion. And then the p-adic integers, which remember are the unit ball, are defined as a subtype of the p-adic numbers. In our definition, we already have the theory of valuations available. So instead of using Cauchy sequence completion, we use adic completion, which is some kind of completion where we are using the theory that we have for valuations and for uniform spaces and so on. And then, perhaps more importantly, instead of defining set P only as a subtype, we are defining set P as the valuation subring. So again, this is the unit ball. These are the elements with valuation less than or equal to 1. But now in MATLAB, we already have some results about unit balls. So by defining it this way, we can access all of these results. So in our project, of course, we want to make sure that what we did is equivalent, so we are providing isomorphisms. Yeah.
So the argument you're mentioning as well, there was already some kind of theory there.
Yeah.
For example, about the unit balls that you wanted to leverage. But did it really make your, do you have a sense that the proofs are simpler because of that choice, or would the proofs be harder if you would stick to the quotient sequence definition?
Well, it's not the only reason that we can use valuation subring. So another reason is that when we consider extensions of valuations, so we consider, for example, some finite extension of QP, and again, over this bigger extension, it makes sense to take evaluation and take the completion with respect to that evaluation. And I think that will be much harder if we were trying to use the definition of Cauchy sequence that we had in MATLAB. I think it will not fit well into the general picture if we were not trying to use adic completions everywhere.
So sorry, do you mean then that is the valuations that we actually want to have as a main objects of study instead of the Piagets? So
what I'm saying is that for what we wanted to do, it was more convenient to use this because we have adic valuations on, not just on the Piagets, but we have them in, well, in the generated that is in MATLAB, is in any Dedekind domain, and any maximal idea you can construct the corresponding valuation and the corresponding completion. And then, yeah, it works together with that theory. But it will, yeah, we initially were trying to use the MATLAB definition because it was already there. And you can make it work, but it's you have to like make things compatible. And if you define it this way, then it works much more smoothly from the beginning. Yeah.
Have any of the definitions that depend on this QP made it to MATLAB? Like, has MATLAB had to address this issue
We
yet?
have not arrived to PR in this part of the project yet. We will get there at some point, and what we are proposing is creating, so in MATLAB we have a class is R or C, and this tells you that some field is isomorphic to the real or the complex numbers. So we are thinking of creating a similar class is periodic, and that will tell you that something is isomorphic to the periodic numbers in some sense. And then we would like to show that both of these definitions satisfy this is periodic class, and then you can work with either version of the definition.
For this, wouldn't you rather want to have something that says is adic completion to say that like p-adic type is the adic completion with respect to the ideal that you have, and then that way you can still have all the, like you can define the evaluation subring and all of these things, but where the underlying types are actually the original types.
Yeah, I mean, I think that's what I'm proposing, yeah. I mean, I call it this periodic, but you could make it more general, I guess. Yep. Yes.
So here, the way I interpret the definitions, the assignments are actually corresponding to Muscovaci's recursion systems of assignments. And when you declare that, for example, PADIC or QP is of corresponding type, so these are the type assignment. This corresponds to the such that operator. And then actually you take this Q, P of type star, it will be taken as an assignment outside. One additional decomposition you have. So you have, for example, Q prime of P gets this value assigned in it, and Q P prime gets the assignment or is such that it is a type. star. So you have here two levels. One is assignment, recursive assignment, and the other one is restrictor. Two things are put together.
I'm not sure about that, but maybe we can discuss it over coffee. I'm not sure I understand what you mean. Okay. Yeah, perhaps I should stop. So I have a couple more comments here, but I will skip them. I will just say that for future work, as I told you, this is part of a bigger project to formalize local class field theory, which is studying abelian extensions of local fields. It's used in Fermat's last theorem. It's also the first case of the Langlands program, which is maybe some buzzword that you might have heard about. It's a very big research program in number theory, and this is one of the few cases that is actually proven. And the proof is relatively complicated, so we are going to need some ramification theory, which is the part that we are working on right now, some homology theory. For that, we will need some work of Amelia Livingstone as well, and we will need to develop a theory of class formations and probably many other things. Okay, yeah, this is everything that I had today. If you want to look at the project, everything is online. Thank you very much.